This video is going to show you how to draw a spur gear with an involute tooth profile in SolidWorks. You could use the same basic process in Inventor and Pro as well. First thing we'll do is create a new file. And again, we're going to use an additive process. So we're going to draw the smallest circle that we need to represent this gear and add the actual teeth on top of that. So doing so, we're going to be drawing the actual addendum circle first and then adding teeth on top of that. Before we can draw the addendum circle, we need to actually determine the size of the gear that we want to draw. In this case, it's going to be an 18-tooth gear with a diametric pitch of 2 teeth per inch. And so we can start off on the front plane. We're going to sketch on this plane, and we'll draw a circle. Now, if we were to draw the pitch diameter, it would be 9 inches, and so that's a good place to start, but we're going to have to make it a little bit smaller to draw the addendum circle. And so to make this the correct size, we need to actually derate this slightly, and it's going to be using the formula of 1.25 divided by the diametric pitch. So 1.25 divided by 2 is 0.625. That's the amount that the radius changes. So to account for the diameter, we can subtract off 2 times that. And there is our addendum circle. So we can extrude this to whatever diameter that we want to draw the gear set at. In this case, I'm going to make it 1 inch thick. And there we have the base circle for our gear. The next step is actually the most complicated, and this is going to be to draw the actual tooth profile. And we're going to draw half of the tooth profile to save some time. We're going to draw it on the exact same plane that we drew the last sketch on. And we're going to focus on where the tooth is actually on the top of the gear. Now, one thing to remember is that the tooth profile is actually determined by the base circle, not the addendum or the addendum. And so we need to draw those actual circles in here, but they're going to be as sketches and not as actual lines that we're going to use to extrude the tooth profile. So the first thing I'm going to do here is actually draw 3 more circles that represent the base circle, the pitch circle, and the addendum circle. In SolidWorks, I can click all 3 of those lines and set them to be for construction only. Now, since this is a 18-tooth gear with a 2 teeth per inch diametric pitch, that means that our pitch diameter is 9 inches. Our addendum is going to be 9 inches plus 1 divided by the diametric pitch times 2 to account for the diameter. So that'll be 10 inches. And the diameter of our base circle is going to be the diameter of the pitch diameter times cosine of the contact angle. And so here you have to decide what your contact angle is. We're going to use 20 degrees, so it's going to be 9 times cosine of 20, which is approximately 8.457. So here we have our 3 actual diameters that we need to define the rest of the tooth profile. We're going to use the base circle to actually draw the involute curve, and the process we're going to use is using the tangent process, where we draw multiple lines tangent to that base circle, and we draw a spline on the end of those. Now, each one of those lines is going to be twice the length, and to generate those lines, we're going to draw segments first. Starting at the center of the gear, we're going to use a center line, basically a construction straight line, and we can go straight out to the base circle. And now we don't want to snap to anything because we want to make sure that these can float around that line. So I'm going to draw 1 line, and I'm going to keep drawing lines. Probably need about 4 or 5 of these at least. Now, one of the criteria is that these lines all have to be the same spacing apart, so they basically have to represent equal segments. You can do that using dimensions, but in this case we don't want to fix them, and so it's probably easier to actually draw another segment line between these points, just as a straight line, and then we can set the length of all those lines to be equal to each other, so we can use a relation without defining the actual dimension. So if I select those individual line segments there and say that they're all equal to each other, now if I move one, the entire assembly will move along with it. So this is what we're going to use eventually to actually position our involute profile in the right spot. So right now it's going to kind of be drawn arbitrarily. And I'm going to go ahead and draw one more of these just in case we need an extra one. So basically our spline is going to start at this point here, and it's going to work its way away from it and curl towards the left-hand side of your screen. And what defines the rate at which that spline turns to the left is going to be a variable radius curve. It's going to be based on the distances to the other segments. And so what we start doing here is drawing tangent line segments. Now I'm going to draw them arbitrarily at first, and then we'll make them tangent using relation. So in SolidWorks, if I click on a line and I click on the circle that I want it to be tangent to, I'm given several options. I'll pick tangent. Note that it actually changes the length in this instance, so we'll resize these correctly later. So now all of our lines are tangent, and again, if we move this system, those relationships are preserved. Now, the basic rule for defining the length of these lines, these tangent lines, is that the first line off of the second point has to be the same length as the segment distance between the first 2 points. And so we can make this line here and that line equal to each other using a relation. Now we haven't defined the actual length at this point. And the next step is to make this line here twice as long as the previous one. And really the only way to do that in SolidWorks is to either dimension them explicitly and know what those dimensions have to be, or we can use a relative dimension. So to do a relative dimension, we have to specify one of them. So I'm going to specify this dimension here, and make sure that you do the actual line dimension, not the distance in the x direction. So we'll make sure those lines are snapped correctly. And now the actual value here doesn't matter so much at first. You're going to see later on that we can change this, but I'm just going to set this to an arbitrary value. We'll make this 0.5 inches for now. And you can see that kind of brought everything in together. And so I want to make the next line twice that without saying that it's exactly 1 inch. I wanted to set it as an equation. Well, the way I can do that is actually click on my original dimension, and I can set this as a global variable. It's going to maintain its 5-inch length for now, but I'm going to say it's equal to some value. So we'll just type it in value as a variable. This number here, this text does not matter, but it's going to save that consistently. So here it's asking me if I want to create a new global variable named value. Yes, I want to do that. And so now we can see a summation in front, which basically means that this is a global variable. And if we go to our actual feature manager here, we can see there's an equation now of value equal to 0.5. And I can change this value, and that value will also adjust accordingly. So if I want to set the next line to be twice that, again, I make sure that my snaps are in the right direction, so that it's the actual line segment. And instead of dimensioning that, I can say it's equal to value times 2. And now it's set it equal to 1 automatically. Next one's going to be value times 3. And the last one is value times 4. Now it looks like I might have missed one along here, so let's figure out which one did I not grab correctly. There we go. So to see that line, I'm going to rotate this slightly. We can can see which one was in there. So I left out one in between. That's easy to change. This one here should have actually been value times 3. That's value times 4. And value times 5. Alright, so you can kind of see that profile already starting to be formed here. If we look at the intersection of all these line ends now, that's our involute curve. One of the neat things is it really doesn't matter what this sector spacing is. All that's going to do is change the way these are approximated. And so I can change this dimension here from 5 to something else. Let's say 0.625. And now it's going to initially not work until I hit the check button. But now you'll see that they all have been adjusted accordingly, and it follows that exact same profile. And what you want to do here is make sure that the entire line segment that you're going to generate crosses all of the other circles that you're going to be intersecting with. And so we have our addendum circle that we need to at least get to that point. Now what's difficult is we can't make this point line up exactly on that circle using this method because we're only specifying this dimension. So we're going to actually have our spline go past that and then trim it later on to make it work correctly. But as long as this point up here is past our circle here, then we'll be okay. And so the next step is going to be to actually draw the spline. So if we choose the spline tool, on SolidWorks we can basically click multiple points along the way and it'll form the spline. And when we get to the end of it, we'll double click to indicate that that's the end of the spline. So now we have a line segment. Now one of the tricks here is that we can trim this and remove that last segment and it'll actually draw the rest of the spline. But if we want it to be dimensioned correctly later on, you'll see, I'll do it again later, we probably want this to actually be a construction line and then we can draw the remainder spline later on. So I'm going to make this a construction spline. So we actually have our 20-degree pitch angle on this tooth, but the last thing is to figure out, well, where does this tooth actually go along the gear itself? And so that's going to involve knowing what the actual tooth width is. The tooth width can be calculated either by the circular pitch or the diametric pitch. And so if you start with the diametric pitch, which is 2, we divide pi by 2 and we get 1.57 inches. Now, that's the actual width of a tooth, but we're going to have 2 teeth meshing together, and so we need to make sure that half the space is allocated to one gear and half the space is allocated to the other. And so we divide that value by 2 again and we get 0.785 for the actual tooth width of an individual gear. Since we're drawing a single gear, since we're drawing a single tooth and half of that tooth actually, we need to divide it by 2 again. And that's going to represent this actual quarter length here. So it's going to be a sector length. It's not going to be the actual point-to-point length. And to actually figure out what the length of that sector is, we actually have to use a little bit different equation. Now, unfortunately, most CAD programs don't allow you to define the length of a curve. You have to define the radius of it. And so we can do that directly. We can actually draw a line intersecting with the vertical axis of our gear. And again, I'll make this a sketch line, so it's not going to be or a construction line. It's not going to actually show up in our final part. And then we need a line that indicates the half of the width of a tooth. And the key is going to be figuring out, well, what's this angle here? And so the relationship between that angle is actually fairly simple. It's the sector length is equal to the radius times the angle in radians. Well, we're going to be working in degrees, so that's not too difficult to convert back and forth. But in this case, we have our tooth width, which is 7.85, and our radius, which is 4.5, and again we divide that by 2, so 7.85 divided by 4.5 divided by 2 times 180 over pi gives us 4.997 degrees. This is where the actual spline has to intersect. And let me move this all out of the way so it's a little bit easier to see. So we want to actually make this spline intersect with that point. And just to be sure, yes, this point is fixed on the pitch diameter. So we can click on our spline, we can click on that point, we can make them coincident, and now everything is actually fixed. So we actually know the exact positioning here. So the last thing to do is just to draw the tooth relative to this spline. So we select the spline tool again, we click on the points that we want to draw, now here we don't actually have a point yet, so we can click on this last point and we can trim the end. Now you can see something happened here. It removed the relation. So we have to make sure that this point and this spline are coincident. That's why you actually have to have the construction spline out there to make sure that you want to fix this geometry. Now if you're not concerned about defining your geometry completely, then don't worry about it, but it's good to make sure that it is fully defined. So here we have the actual line segment. It's a little busy, but you can see the dark line here is the actual tooth profile. Now I said before that we're going to be drawing half of a tooth, so we can split the tooth in half down the center. And here we can actually use the convert entities to fill out the bottom part and the top part of the tooth. So I'm going to click on this outside circle, we'll convert that to an actual entity. Oh. Well, I guess I'll be drawing it by hand. So we're going to draw an arc here and we'll make it concentric to the other. You could also use co-radial in that instance. And so that fills out the top part of the tooth profile and it's fully defined. Now look at that, I found a little spot that shouldn't have been there. That's an interesting feature, so we can actually force that point to be on that line. Whoops. Let's undo that. There we go. So the last thing that we have to figure out now is actually how the end of the tooth connects with the rest of the gear system. And so we have our clearance down here on the dedendum, but there has to be some type of connection between here and there. And so I can fill in the bottom half using the convert entities feature, and we can trim off all that later. But we have to have some transition from here to there. We could just follow this straight line, but that probably wouldn't be a very strong tooth profile. Generally what happens is you go down a little bit and then you have a radius here. And so one of the things we want to make sure is that the radius doesn't intersect with the next tooth profile. So I will draw a short segment here, and then I'm going to draw a 3-point arc that connects that segment to our dedendum. I'm going to force that arc to be tangent to both surfaces. And so this will actually be the midpoint between teeth, and I can define that exactly. I know exactly what the tooth width is. I calculated it before and used an angle to do it. And we could do the same thing again. So I can actually draw a center line from here to here, and I can specify that angle. And it's going to be twice as much as that previous angle. Now again, that wasn't exactly 5 degrees. That was 4.997. And so if I multiply that by 2, I get 9.994. Now as soon as I define that, that should define the rest of my features. And so now we have a pretty heavy radius on here, but the nice thing is as long as there's a little bit of space between here and there, we'll have plenty of clearance on the tip of our tooth. So this entire sketch is complete. We just need to remove the rest of this line to be able to extrude it. I'll use the trim tool in this case. And now since I have all these other lines, I have to trim every single one. But once we get on the outside, it will trim the entire rest of the segment. So now we have a complete sketch. We should be able to extrude that if we've done this correctly. Oops, looks like we made a mistake. Let's go back and figure out why that happened. We'll delete this feature, revert back to the original sketch. It looks like there's actually a line segment up here that got left over that we need to remove. There we go. Let's try that again. Oh, there's still something left over again. So that was an issue with the trimming feature. There was actually a line coming up here, and I left over a piece of that line. You got to make sure you trim all those individual lines, otherwise it doesn't know exactly what's going to be the part that's extruded. So there you have half of a tooth profile. Let's look at this from the front view. So now really all we have to do is actually mirror this part across our right plane, and then we can circular pattern it around the entire gear and add a hole to mount the gear onto some type of shaft. The mirror is a relatively easy feature. We can pick this feature here, the boss extrude. We can pick the right plane. We can go to mirror, and it automatically populates the right elements, and hit check to hit OK. So now we have a full profile, and so it actually maintains these surfaces correctly as well too. So you can see the involute tooth profile, the top face of the gear, our flat end there, our radius, and so that's an entire tooth profile. The next step is just going to be to circular pattern that. So we can pick our boss extrude, our mirror, and do a circular pattern. Click on the circle that we want to revolve that around, and it's just a matter of picking the right values. And so again, this is an 18 tooth gear, so we already happen to have 18 there. Right now the spacing is not correct, and so if we take 360 degrees and we divide it by 18, we end up with 20-degree spacing between teeth. So if we change that to 20, now our teeth are actually spaced correctly apart. And since we specified this point here, these two curves should form a single radius. Now, again, this is an approximation that we did round, and so it's possible that there'll be a little bit of an edge here, so it won't be a continuous curve, but that's not going to be a big deal. So we hit check to finish that profile. Now we have our actual gear drawn, and again, we have a complete involute profile. So this is not an approximation of several lines. This is a nice variable radius curve. Last step, we'll cut a hole in the center of this. We'll put a 1-inch hole. And we'll cut this through the entire surface of the gear. So there you have it, an 18 tooth, 2 teeth per inch Involute Spur gear.